Welcome back. This is Systems 522, Fundamentals of AI, taught in the University of Waterloo in the fall of 2023. I'm Terry Stewart, and this is Lecture 1, the Perceptron. This is sort of the first of the core content of the course. There was, of course, Lecture 0 last week. But this will be getting into the beginnings of neural networks and sort of the foundations of modern AI. And what so the perceptron, the predictive model that we're going to be talking about today, it's not technically the first neural network. So neural network, so this whole idea of I have a bunch of small components, I'm going to connect them together. Those connections between them are going to have some sort of strength, some sort of connection weights between them. That idea had been kicking around for a little while, probably starting McCulloch and Pitts, 1943. Most of the time, though, when they were talking about those sorts of networks, they were talking about a hand-designed network. So you're like, okay, I'm going to have these components, I can connect them with these strengths, and oh, okay, I can design this to do some particular task. And that's a whole fascinating field, separate field. It's sort of outside the scope of what we're talking about in this course. It is like the foundations of a lot of things in computer science, so finite state machines, regular expressions, a lot of sort of like these early stages of computer programming fits very much or comes out of that line of research. But that's not what we're talking about here. What we're going to be talking about is sort of the first time where we've got a bunch of these basic components, but I don't have to hand design things. I can set up a structure, and then I can have the system itself sort of adjust itself or learn to do something somewhat on its own. Okay, that's going to be the core new idea here. This probably got codified. I mean, these ideas have been around over that decade, but it's sort of codified in a paper by Rosenblatt, 1956, called The Perceptron. And it got so much excitement and so much sort of interest that they went ahead and built a physical machine that implements this algorithm. So the picture there on the bottom right, that is the Mark I Perceptron. So over here, 1958, this machine is up and running. It's one of these. It's not quite room size, but very, very large computers, and it can do image recognition. So it has a 20 by 20 input. The one way to think of the input is sometimes they would use it as like an image input where you're holding up a piece of paper and it sees bright spots and dark spots. It's pretty limited back then, so the inputs are like, it's a 1 or a 0. It's not quite grayscale. Or you have just a bunch of switches you can flip, and so you can set the switches in order to set what the input currently is. And it was quite capable of recognizing images. So how did this work back in 1958? All right. So what's the algorithm? All right. So here's one way that it was sort of written back then. We're going to adjust the notation in a moment. But the core idea is there's going to be some things. We're going to in this particular case, we're using phi to indicate those things. So 1, 2, 3, up to n. Each of those things is going to get multiplied by a weight, alpha 1, alpha 2, alpha 3, up to alpha n. All those values are going to get added up. And then we're going to compare that output. If we're going to see, okay, that value that's added up, is that bigger or less than theta? And if it's bigger, then we're going to output a 1. And if it's less, we're going to output a 0. Okay, so that's another way to write that is over here. I'm going to adjust the notation slightly, just to be a little bit more moderate. So we're just going to be thinking, okay, we're going to have the x's. Those are the values coming in. We've got these weights, which sometimes I'll write as a w, sometimes I'll write as a lowercase omega, which looks an awful lot like a w, so it's hard to tell the difference between those things. That's going to get added up. We're going to compare to theta, and that's going to produce our output. And the output's going to be a 1. If it's greater than theta, 0 otherwise. Okay. All right. That's a reasonable structure. What can we do with that? That seems Okay, so if I have some data, then that gives me the x's and the y's. And so in order to program this to do something, I'm going to need to adjust the weights and adjust this theta parameter. How are we going to do that? Okay, well, here's the learning rule. So here's the core idea. So this is going to be an example of supervised learning. So this is a situation where I've got a bunch of data, and for each data set, I know, given this particular input, this particular set of x values, I know what the output is supposed to be. Okay. So the idea is going to be, fine, let's just initialize it with random weights or zero weights, or just put these weights to some value. Feed in an x value. Feed in a particular set of data. So say I've got 3 inputs, and maybe those are these 3 inputs right here, x1, x2, x3, and so x1 is currently a 1, x2 is currently a 0, and x3 is currently a -1. So those are the 3 values I'm shoving in. And let's say in my data set, I know that that particular value, the output is supposed to be a 1. All right, I'm going to apply this input. All right, what's the math of the perceptron? Okay, it takes each of these inputs, multiplies them by a weight. So 1 times 0.2 plus 0 times 0.3. So 1 times 0.2, that's 0.2. 0 times 0.3, that's 0. So we're at 0.2. Minus 1 times 0.4, that's minus 0.4. Add that in, so it's a total of minus 0.2. And let's just assume that the theta is 0 right now. Minus 0.2 is not bigger than 0, so my output is currently a 0. Okay, that's what the perceptron rules, or that's what the perceptron is doing. But that output is wrong, and so I need to adjust the weights. And so how am I going to adjust these weights? All right, well, they're just numbers, so my only options are increase them or decrease them, or I guess keep them the same. I want this sum to be a bigger number. Right now, the sum is too small. And so how should I adjust this weight here? I've got these 3 weights. Let's just start one of them. That weight right there, how should I adjust it? Well, if I want the sum to be bigger, and this weight is being multiplied by 1, then I should increase this weight. If I increase that weight to, 0.3, then my total sum is going to be bigger than it was before. All right? So I want to increase that weight. Cool. Well, what do I want to do to this weight? Well, changing that weight isn't going to do anything at all, because changing this weight is going to get multiplied by 0, so changing that weight makes no sense at all. Let's just leave it how it is. And this other one down here, this this 0.4 weight, well, it's getting multiplied by a negative number. If I increased it, that would make my sum smaller, so I want to decrease this. Okay, so let's sort of make some intuition as to how we would want to adjust these weights. Cool. So how do we're going to codify that as sort of a rule, and this is what that rule is going to look like. Okay, so the change in the weight, the delta of a particular weight, first thing we're going to do is going to take the difference between what we want the output to be minus what it is. Okay, if the output is supposed to be a 1 and it currently is a 1, then the difference between those things is going to be 0, and the weights are not going to change. Right? If I want it to be a 1, but it is currently a 0, fine, I need to make things bigger. If I want it to be 0, but it's currently a 1, fine, I need to make things smaller. So that's what that part is going to do. And then we're going to multiply it by xi. That's going to be the equivalent of what we were doing over here of saying, oh, hey, look, leave things the same if x is 0, increase them if x is 1, if positive, decrease them if x is negative. Okay, so that's going to take care of that part. And then we've got this little extra thing of like, well, how much do we move it by? Do we move it by 0.000000001? Well, sure, we could do that, but then it's going to take a long time to learn. Do we move it by 1,000? That's probably a bad idea. Don't increase the weights by plus or minus 1,000. That seems like a big number. Pick something in the middle. Okay. Most of the learning rules we're going to run across during this course are going to have something like this sort of how much do I adjust by. that's called a learning rate parameter. Oh, for some reason, there's tons and tons of different variables that you use. Sometimes it's eta, sometimes it's lambda, sometimes it's gamma, sometimes it's alpha. Here I've got it as alpha. It's just a scalar. It's just a number that we're just going to multiply the rest of this by and say, okay, that's how much I'm going to change my weight by. And the general rule of thumb is you pick too small a number, it's just going to take forever. You pick too big a number, it's going to have problems learning. And we want some sort of median value. There will be more to talk about that later in the course, but that sort of idea is there. Okay? So this seems like a system that should go ahead and adjust the weights and make them bigger or smaller and try to, get better at the tasks that we're giving it. Okay. And yeah, so, you first play around with that on paper, and then you're like, okay, this algorithm seems really good. Let's go build a computer. And so they went and built this big computer. Now, of course, there's fascinating questions about how in 1958 you go about implementing this sort of learning rule. Heck, even just this sum up here, how do you implement this part? Well, what you can do for that sort of thing, I don't have modern computers back in 1958. So they're actually doing this fully in analog. So what they're doing is, this equation here, this is sort of, you can think of this, well, if I have a bunch of voltages are my x value, and these weights are resistors or conductances. So, so they're, literally just attach the voltage to a resistor. What that's going to do is it's going to multiply. All right, and then if I have, that's going to create a current that is the product of the voltage and the resistance, or voltage and the conductance. All of those currents, if I then connect them to the same point, well, that's going to add them up, right? That's just because currents flowing into it, the circuit, the currents are all going to add. And so I can use that to go ahead and go do that computation. But then becomes this question, of course, is, well, how do you go ahead and implement this learning rule? Because what that learning rule is, what they'd be doing is they would be changing the resistance. Fun thing you can do there is you can go ahead and there are variable resistors, potentiometers. And what those looked like back then is they're sort of like a cylinder that you could twist, and as you twisted it, it would change the resistance. Okay. And so, in order to implement this learning rule, they went ahead and attached motors to those variable resistors, and then powered the motors based on, of course, this part of the learning rule. So the system would sit there when you sort of, all right, here's an input, here's what your correct value is supposed to be. That would power up the motors, and they would twist the motors and adjust adjust the weights to what they should be to make it work. Okay. So fascinating, interesting challenges of trying to actually build these things, build all these learning systems without modern computers. That was the approach that was taken. Built this big giant machine. And before actually showing how it works, I do want to highlight one little thing. In a lot of these, and certainly in these sorts of models, and in a lot of neural networks, you have these things like both weight. You have different types of parameters you might want to modify. The learning rule I just described tells me how to modify these weights. But I haven't yet described how to modify this theta value, this threshold parameter. And what we're going to do is we're going to use a little trick that is sort of pretty common across a lot of AI models of well, hold on a second. It would just simplify my life a lot if I could just write this such that everything is weights, and I don't have to have two separate rules, one for weights and one for theta. And the way we're going to do that is we're just going to sort of, all right, pull the theta over to the other side. And now that I've written it this way, I could bring this into the sum. And the way I could bring this into the sum is I can say, okay, well, let's imagine there was another input that is just always set to 1. And then instead of calling this theta, I can call this omega 0. So if I've got this input that is always set to 1, we'll call that x0. And I've got this, instead of theta, I could have this other weight that is for this first parameter. And, that weight, whatever that weight is, that's the negative of whatever theta is, that's going to cause this equation to just be exactly the same as above, right? We're just summing over a larger range. So, standard trick that'll be around there. Anytime there's a bias term, and you're like, I have a bunch of weights, let me just go bring it in there. You can always just shift it over to be one of the weights by sort of pretending that there's an extra input that is just always set to 1. All right. Doesn't really matter. Small little trick, but it just means that we don't have to define a separate learning rule for theta. Cool. All right, let's go ahead and try this. Here's some data that I want to try it on. What is this data? So I have a bunch. So each of these points, so we've got x1 across one axis and x2 across the other axis. So the inputs, I have 2 inputs that are being fed into the system. And each of these dots is a different input, and the color of the dot is indicating what output I want. Okay, and so, I don't know, with, if I want, so the blue dots, maybe I want the output to be 1, and the red dots, I want the output to be 0. And I've just randomly generated this data. So that's what we want our system to do. I've just generated a bunch of points, and fine. Let's start our learning rule. And I'm going to start this perceptron with some weights. And the particular weights that I'm going to set it to are what I've got up here. So I've got the weights to be 1 and -1. And that bias term, that theta value, I've set to just be 0 for now. Okay, so that's what it currently is. And now what I'm going to do is I'm going to take that normal perceptron learning rule, the perceptron algorithms, or the equation, this thing over here, okay, and I'm just going to compute that for all the different inputs. Okay, oops, there we are. And that's what I'm going to use to color it. So this is what I want. This is what I currently have. So it's got about half of them right, but I haven't trained it at all yet. So all I've done right now is I've just set those weights to just arbitrarily picked numbers, and now I still need to actually train it. Okay. All right, well, before I train it, there's sort of an interesting pattern in this data, right? That, like, it's not just sort of randomly red and blue dots all over the place. I haven't given it any information about the system itself, so I haven't done any training. I've just set the weights to some arbitrary values that I've chosen. And there seems to be some sort of interesting structure here. In particular, there seems to be this kind of straight line sort of through this. Okay. And there's a reason for that straight line. And one way to think about that straight line is if you think about, well, okay, what math is happening here, right? So the line that is going to divide these red dots, or sort of the red dots from the blue dots, that's going to happen when that sum, so x1, omega 1, x2, omega 2, that's the sum that we're computing, right? And then we're comparing that to theta. Is it bigger or smaller? If they're exactly equal, well, that's going to be the line where we go from red to blue. Or that's going to be the place we go from red to blue. Haven't yet shown that it's going to be a line. If I want to argue that this is going to be a line, well, if I look at this equation, and I do a little bit of rearranging, because x1 is on this axis, and so and then x2 is on this axis. If I do a little bit of rearranging, and just rearrange things for x2, that's the equation of a line. Right, so that's, from high school when you have y equals mx plus b, right? That's exactly mx plus b. Of course, we got x2 is in our y-axis, but fine. Right. So what this is indicating is no matter what we set these weights to, this dividing line that separates things in the category from things not in the category is always going to be a straight line. Now, it's a line in this two-dimensional case, just because, well, we've got 2 dimensions, and so it's going to be a line there. In 3 dimensions, if these points, so if we have 3 inputs, then there's going to be a plane in the 3-dimensional space that's going to cut things in half. There's always going to be this sort of slice through the data, and everything on one side of the slice is going to be in one category, everything on the other slice is going to be another category. Okay, that's just a mathematical rule for, if this is our learning rule, or sorry, if this is our decision criteria, right? If it's some sort of, hey, I'm going to do some sum like this, and I'm going to compare it to some number. If that's what I'm going to do, that's always going to make a straight line division between our data sets. Okay. All right. So we know that's going to happen. So I'm going to add it to my diagram just to make it, just hopefully for clarity. So I just take a look at those weights. Okay. And I can just compute what the equation of that line and plot it. All right, and yes, everything on the one side. Oh, and then I'm also shading the 2 regions, just again for pretty. So what that's just indicating is that, yes, even though these are the actual data points that I have, this system will classify anything in this blue area as in that one category. Like I said, putting as a 1, and everything in this area, it's going to output a 0. Okay. All right, so that's what a perceptron is going to do. What happens if we start learning? Okay, so what do we mean by learning? Again, we pick one of the data points. We see if it's classified correctly. If it's classified correctly, yay, we don't change anything. If it's classified incorrectly, then we go ahead and change the weights based on the math that we were showing. So we do that a few times, and the line moves. Do that a few more times. Do that a few more times. And now we're at a spot where it stops changing. Because all the data points are classified correctly. Right? So the line is no longer going to move anywhere. Okay. And we can even go there, see what sort of the weights and the bias value that it's gone ahead and set up. Cool, so that works. One sort of slightly annoying thing here is the solution's not actually going to be unique. There's lots of different lines that you could draw that would divide these 2 data sets. Where we draw that line is not going to matter for how good it is on this data that we're saying, okay, here is my training data. Here is the set of data where I'm like, okay, these inputs should produce these outputs. That's not, each of these solutions are equally good in terms of how well they do on the data that we have. But the reason I'm sort of drawing this way is you'll notice that these 3 models are going to generalize in very different ways. Okay. So if I in the future got a new data point that was, say, here, then this version would classify that as red, whereas this version would classify it as blue. Okay. We'll be talking about that later on in the course. How do we start dealing with sort of issues like that? Are there ideas about, well, what's the best line you could put through there? With the perceptron learning rule, though, it's just going to stop once everything is working. It's saying, okay, cool. For everything I know about, I'm as good as I can get. Let's stop adjusting anything. Okay. Which maybe is fine, depending on what our task is. Okay. And then, like, what causes it to be one of these lines or another? Could just be like the random order that you choose the points in. Could also be your learning rate will also affect this. And very hard to predict, which of these is going to lead to which outcomes. So the only thing the point is, the only thing the perceptron learning rule guarantees is, hey, if there is a way to draw a line between these 2 data sets, it'll find it. Awesome. We have a thing that can learn. Right, that example there was just for one, right, well, 2, I guess, one category, so in the category or not in the category. If you have more than one category, so if you have 2 categories, 3 categories, say, might be the more interesting one. So if there's 3 different categories I'm trying to put things into, A, B, and C, I can do exactly the same learning rule. We just sort of have 3 outputs, and we just learn each of them independently. One of the outputs is just, is it an A versus not an A? And the other one is it a B versus not a B? And is it a C versus not a C? Okay, so nothing particularly interesting to say there. It's just easy to generalize to more than one category. All right, so cool. We've got this big thing that can automatically adjust its own weights in order to learn a particular thing. Can it learn any given pattern? And I hope you're somewhat worried about this question. And here's sort of one classical situation where you're like, well, hold on a second. If, say, my data set looked like this, I've got, these two data things. Go ahead, draw me a straight line that separates those two data points, those two data sets. The perceptron will learn one if there is such a thing, but how are you going to know? This is just not going to do a good job of this. All right. However, this is less so. The answer to the question, can a perceptron learn any given pattern, is actually yes. A perceptron, as it's originally defined, can actually learn any pattern, even those ones that I was just showing there. And that's because I've been lying to you so far. The perceptron is more than what was drawn in this particular diagram. The perceptron actually looks like this. Okay, so over here, the right-hand side of this diagram, yeah, that's what we've been talking about. Okay, but right from the beginning, when this thing was initially invented, everybody knew, because of this linear separability problem, that there's no way you should run this algorithm on the raw input data. Okay. You have to take your input data and first transform it in some way, and then as long as you've, for any possible task, as long as you can transform it, then you can always solve things. So if you find the right transformation, the right way to convert x into a bunch of functions on x, then we can always find a way for the perceptron to learn whatever pattern you want. And I mean any pattern. So that includes things like, I don't know, here are a bunch of pictures, and please classify them as cats, dogs, and elephants, right? Or here are a bunch of essays. Please classify them as good essays or bad essays, right? As long as I have some training data, it can find a way of if I have some training data, those are my x's and y's. There is always some way of transforming that data such that then from this point here, I can then go ahead and do that automatic learning rule and learn the weights and make this all work. Okay. All right, so how do we deal with this particular problem up here as sort of an example? Well, what we can do is fine. We've got two features, x1 and x2. That's where it is on the x-axis, where it is on the y-axis. Let's compute a third feature, a third value out of those. Terminology. Let me go back here. We often are using sort of the raw data is sort of how we'll refer to the actual input, and then these things here, the things we're going to transform it to, we could refer to as features. Okay. Now, some of those features could be the raw data. All right. So one thing I could do is I could say, okay, one of the features is, feature 1 is the first element. My input is 2 values. Feature 1 is the first value of my input. Feature 2 is the second value of my input. And feature 3 is something that I compute off of those other values. And one particular thing that would work really nicely for this data is if I went ahead and computed feature 3, which is square root of x1 squared plus x2 squared. What's that? That's the distance these things are from the center. Right? That just seems to be that. Just looking at this data, that might be a nice feature to separate these things out. If I go ahead and do that, well, now I have three-dimensional data, and if I plot that three-dimensional data, it looks like this. And that three-dimensional data has a really nice plane that I could cut right through here to actually go ahead and separate this data into two categories. So it's always possible, given whatever data set I have, to find some sort of features that I could add to the system. I could compute and add in this sort of way, such that the resulting system ends up having this sort of linear separability, or linear separability. And as long as it has that linear separability, the perceptron algorithm is guaranteed to find the slice that cuts through that. Okay? That's why people got all excited about these algorithms. Like, oh, this should be able to do anything. So if you have the right features, the perceptron can match any pattern that you desire. Okay. All right, so what sort of things did they end up building? So for the Mark I Perceptron, they this is a circuit diagram from the freaking owner's manual, and there what they actually said is, okay, you know what? It's hard to figure out good features. I mean, that thing back here of like figuring out, oh, hey, look, maybe a good feature here would be the distance from the center. That's hard to do. Maybe we can get away with just sort of randomly choosing the right features. And that is what this mess of circuit wires is over here. Okay, so that's actually what they're doing. These inputs, so there's a 20 by 20 grid of inputs, so there's 400 inputs. And then these features that they're extracting from those inputs, what they're doing is they're sort of just randomly combining elements from that input. All right, so maybe I might take, I don't know, the two values that are next to each other. In this particular design, all of the inputs are either 1 or 0. And so the sorts of things they would do when you sort of bring these two components in is they might, I don't know, take the OR of them, so or take the AND operation of them. So so simple operations of these inputs, they would then go ahead and transform it. That gives me a new value here, and it's these feature values that we then go ahead and do the learning on. So this is where the learning would happen, and then but over here is where the would, you know, in this particular case, just random connections. Or if you knew something about the task, you could go ahead and design these connections in a better way. Okay. All right. So that's the definition of a perceptron. And this is a really strong claim to make, that if you have the right things in the middle, I can match any pattern. Now that really requires some justification. Right? You know, fine. I showed you for this example. I can make it work, but you know, I could come up with some really weird patterns over here. Are you really serious you can make something work for anything? How do we want to go about showing that? So I don't know, here's some random, you know, I don't know, here's some data over here. How are we going to set this thing up? What do we want to put in this sort of black box here, such that I can convince you that we could make this thing work, and we can make the output be whatever, you know, match this particular set of data. Okay. So again, our target is I want to set up this system such that the output, if I give it this input, so the input 0.3, 7, and 4, if I give it that input, the output ends up being a 1. And if I give it this input, the output ends up being a 1. If I give it this other one, output's a 0. The other one, output's a 0. The other one, output's a 0. Okay. And I might be able to just sort of stare at this data and like come up with some feature that I could sort of imagine that might make this work. But I'd like to have more sort of a more principled approach that just, you know, if I really want to be confident this could do anything, how could I make it do anything? Okay. All right. Well, let's do something really dumb. Let's have a feature that is just, is the input exactly equal to this pattern? And let's have another feature that is just, is the input exactly equal to this pattern? And then I can just simply say, all right, if one of those features is active, set these weights, you know, sorry, if one of these features is active, set these weights to 1. That'll cause this thing, you know, set theta to 0. That'll cause this thing to be value bigger than 1. It'll go ahead and output a 1. In any other case, all of these things are going to be 0. 0 is not bigger than 0, so it'll output a 0. So that's sort of the cheating dumb proof that yes, with the right features, you can make any, if someone gives me a set of data, I can always build a perceptron that will exactly match that data. Now, the worry that you should sort of have in your head is like, hold on a second. First of all, this is really dumb. This is a lookup table. This is just I'm just encoding the answers that I want, and then if I give it the question that I've already encoded the answer to, yes, it can spit out the answer. Great. That doesn't seem like intelligence. And this sort of highlights an aspect that is going to come up over and over again in any of these supervised learning algorithms, is the task is not just to make the output match this set of data. We probably also want it to generalize to new situations, so that in new situations it will do something that feels about right. And in this particular case, if I gave it something that it was almost exactly one of these, if I gave it 0.37, 3.9999999, well, that wouldn't be a perfect match. It would not output a 1 for that. And it sort of feels like, with most of these things, like it feels like a small difference. Maybe it should still be robust too. That becomes an interesting question. Is that the right answer? What is the right answer for in new situations? Especially when if the only thing we've defined that we want this to do is just, here's some data, try to replicate that data as well as you can. If that's the task, well, just doing this dumb lookup table is a perfectly good solution to the task. If we want it to do something else, we've got to be a little bit more careful about how we define our task. Again, we'll be getting into that. In the meantime, though, one slight modification of this lookup table thing is, well, what we could do if we really want it to be sort of like, okay, if nearby inputs should also behave sort of similarly, we could go ahead and say, all right, let's have features. There's one feature for each of these inputs, and we'll have it be a 1 if the input is closest to this feature than closest to this data point than any of the other data points. Okay. So then that is going to at least generalize a little bit better. So it's still, again, it's going to perfectly do the task. But now we've got this extra feature that it might generalize a little bit, so that if I give it a data point that is nearby something, it'll go ahead and output, whatever category the nearby, it'll output whatever category the data point that is closest to this is in. This has a name. This is called nearest neighbor classification. This is sort of a really simple classification algorithm. Forget this neural networky stuff. Just have a big data set of all the data that you're training. If you have a bunch of data that says, okay, look, this is a picture of a cat. Here's a picture, it's a cat. Here's a picture, it's a dog. Here's a picture, it's an elephant. And then someone gives me a new picture. I could just compare that picture to all the pictures in my data set, figure out which one it's closest to, and say, oh, hey, look, that one it was closest to, that was an elephant, so therefore this is an elephant. Okay. That's actually pretty powerful classification algorithm. People often sort of generalize that a little bit and go to k nearest neighbor classification. So they'll do things like, okay, instead of just finding the one closest picture, find me like the 3 closest, and whatever category the majority of those are in, that's what I'm going to call this one. Okay, so this is called the k nearest neighbor classification algorithm, and you play around with k, 3, 5, 7, something like that. You output whatever category is sort of most common out of those k. Great classification algorithm. Computationally expensive, because you've got to do a whole bunch of comparisons there, but pretty good algorithm. And interestingly, kind of competitive to sort of modern neural networks. So there was a recent paper out of the University of Waterloo doing comparing the k nearest neighbor classification algorithm on text documents. So I have a bunch of documents, and they're put into categories. Okay, I don't know, this one's this is a good essay and this is a bad essay. I don't know how they're categorized. Okay. You have a bunch of data sets. And then what you do when you get a new document, you want to classify, is it a good essay or a bad essay? You just find the document of the data set that it's closest to. This particular paper does some playing around with what it means by closest to. In particular, it ends up being sort of, well, how good would how much could a text compression algorithm compress the data if you had both of them? But it's still sort of this sort of find me the nearest sort of algorithm. And it ends up being pretty competitive. Like, they compared it against the sort of modern deep learning language, text classification algorithms, and did pretty good. This is still a computationally expensive approach, but the point I'm trying to draw here is that if you've got a lot of data, a really simplistic algorithm like nearest neighbor classification can work really well. And yes, it's computationally expensive, and it's also not particularly smart. Like, some people would be a little bit uncomfortable calling the algorithm of whenever I want to classify something, I just go look in my past about all of the things I've seen before, and whatever it's closest to, I'm going to put it in the same category. People might be a little uncomfortable calling that intelligence. But this sort of really dumb algorithm, fine, deep neural networks might end up doing something different, but it might end up doing something that sort of just approximates this algorithm. That's one way some people think about modern AI systems, is they're just sort of ways of implementing exactly this sort of dumb algorithm, but with less computational resources. So instead of having, because this nearest neighbor classification, every time I get an input, I've got to compare that input to every single freaking one of the inputs I've seen in the past, and that might be a really, really long list, especially with modern systems that are trained on tons and tons of data. And so there's definitely times where if I've got some sort of deep network that's doing classification, and I'm really hoping it's capable of generalizing to some new situation, or is it going to work on this new picture that I'm providing it? One heuristic that I can use is sort of go, hold on, okay, if I did have a lot of compute power and I was doing k-nearest neighbor classification, would that still work on this task? And if it wouldn't, if something dumb like this would not, it's often unclear whether or not a modern neural network would end up working, because a lot of the ways the modern networks end up being trained, as we'll sort of look at, can be thought of as just as an approximation of this sort of really dumb approach. All right, sorry, that was a little bit of an aside, but again, that's sort of in my category of yes, modern AI systems are really, really impressive. So are really dumb algorithms like this. And there's times when you can, fine. Facebook does a great job of recognizing your pictures and putting, you upload a picture to Facebook and it labels who's in it. A perfectly good algorithm for doing that would be, hey, let's just go ahead and take the database of all the other images and go ahead and do this direct comparison. Yes, they've come up with a way that's more computationally efficient than that. But we should sort of keep this comparison in mind when we don't want to think about, are these things intelligent? Let me say a little bit more about that. But first I want to finish off. Fine, yes, a perceptron can learn anything. If you have the right features, perceptrons can match any pattern desired. Okay. But having these features is sort of a key step in there. And that's sort of a really big caveat if you have the right features. As I was saying, what we've got here, the sets of algorithms we've seen, mostly focused on this perceptron thing. That's, fine. I have some inputs. I'm going to convert it into features, and then I'm going to do weighted sums on those features in order to generate a category. Is this artificial intelligence? It seems like it might be a step in that direction. I want to put a little bit of skepticism in there. And some of the skepticism, so in the Minsky and Papert Perceptrons book that came out in 1969 that sort of analyzed perceptrons and is widely credited as the book that sort of destroys neural networks for 10 years. Whether or not that's a warranted statement is a separate issue, but it was certainly something that's sort of an interesting marker of here are the problems with the sort of perceptron type approaches. And then with these sorts of neural networky things going away for about 10 years. So this is the first AI winter that I talked about in the previous lecture. And then also a lot of the other AI methods also not working. That sort of contributed to that, or not working. Not that they weren't working. Weren't generalizing past toy examples. In any case, this particular book has some really harsh statements in it. Things like this one where they're not even saying, one thing I do find fascinating is they're not even willing to call this learning. Okay, they're putting learning in quotes. They're saying, hold on a second, is this really what we mean by learning? They do have a very nice summary of the perceptron, so I'm just going to quickly read that. So the machine is built, the purest version of perceptron is a pattern recognizing device is the following. The machine is built with a fixed set of computing elements for the partial functions phi. Okay, so that's where our features being extracted from the raw data, usually obtained by a random process. To make it recognize a particular pattern, one merely has to set the coefficients alpha, that's our connection weights, to suitable values. And thus programming takes on a pleasingly homogeneous form, as opposed to programming in sort of a traditional sense, or building hardware. Instead of having to build sort of custom code to do one particular task, instead what you're doing is you're always doing exactly the same process. All you have to do is take these weights and adjust them. And the one thing they point out here is that since these weights, since programs, the weights, are representable as points in an n-dimensional space, so that's my set of all of my the values of all of my weights. Since that's mathematically that's a space with a metric. In other words, sort of there's something about points being nearby. So if I change a weight by a small amount, then that probably means that the program's behavior is changing by a small amount. That's what's being said there. Then this makes it easy to imagine a kind of automatic programming, which people have been tempted to call learning. Okay. By attaching feedback devices to the parameter controls, they propose to program the machine by providing it with a sequence of inputs and an error signal, and this causes the coefficients to change in the right direction when the machine ever makes an inappropriate decision. That's exactly the perceptron we were just describing. And I didn't talk about it in detail here, but there is a mathematical theorem, the perceptron convergence theorem, that says yes, it's going to find the right answer if there is an answer. Okay? And it's not going to take an infinite amount of time for it to find the answer. So one thing I really like about that is the skepticism of even calling this learning. Nowadays, it's just sort of everyone in artificial intelligence, everyone in machine learning, by the term learning, they mean adjusting values that are, whether they're connection weights or slightly other parameters, they mean adjusting these parameters. Okay. And that sort of terminology is taken over. It's not obvious that that's the right terminology. When humans use the word learning, we may possibly might mean a lot more things. But we now have sort of developed in artificial intelligence this very technical definition of learning, which means adjusting connection weights. And whether or not that's a nice match to normal use of the word learning is an interesting question. In any case, the focus of this book was breaking down what are the problems that need to be addressed if we're going to use this sort of technique more widely. So it's often so when people ask, "Oh, what's the problem with perceptrons? Why didn't they work very well? What problem was pointed out?" One answer that often gets cited is, "Oh, they can't compute XOR or any other non-linearly separable problem." So that's just an example of the sort of things that I've been showing of data sets that you can't draw a straight line through to separate out the two categories. That's not what the book was pointing out. Everybody knew that, yes, you needed these features. You needed to take your data and transform it in some way, and then you can do, then your perceptron is going to learn perfectly well. Perceptrons can learn XOR no problem. You just need the right features. The actual problems that were pointed out, a couple of them, one of them just sort of focuses on, well, where do you get these input features? Or where do you get these features? Is generating them randomly going to work? Is there some theory for this? How many is going to be enough? And one of the big emphases in that book was pointing out, hey, there are functions that you're going to need features. So if you're going to randomly generate your features, you've got this interesting question of, well, each feature, how many of your inputs should it be connected to? All right. So this particular feature here, and sort of you can see this in the diagram, so this feature here, it's sort of sensitive to these particular inputs here. And this feature is connected to those inputs, these ones to those inputs. All right, that tended to be something they would do when they were randomly generating these things. What the book pointed out is there are some functions, if you want this thing to learn, if you really want to claim this thing can learn anything, there are some functions that require features that are sensitive to everywhere in your data in your data set. Okay? You need features that are sensitive to all of your inputs. Okay. One particular example of those functions. So if you ever do find a copy of this book, this is the cover, or one of the covers. There was also a circular version, and what it's actually depicting is exactly one of those tasks that you need features that are sensitive to everywhere in your entire input space to distinguish. And this particular task is, all right, I'm giving you a picture. Is that one line or two? All right. So for one of these, if you sort of trace out exactly where this line is, it's all one continuous line. And for the other one, and I don't even know which way around it is, for the other one, it's actually two lines that are sort of twisted around each other. Okay, and that particular task, they end up proving, I need to have, if I'm going to do that task and distinguish between those two things, this is a task that humans can do, I'm going to need to have features that are sensitive to all the inputs. So I don't even know, it's still a separate question, even if you're going to do this of like, well, what function do I compute on all of those inputs? That's a separate question. But it's also demonstrating you're going to need some that are sensitive to all of them. Okay. That's going to be a problem if I'm going to do some sort of approach like randomly generating my features, because that's just going to mean I'm going to need so many features. Because there's just many ways of grabbing all of these data. If this is 20 by 20, there's 400 data points there. There's like 2 to the 400 different pattern choices of which of these elements to choose a feature can be connected to. Those are really big numbers. Something's got to deal with this problem. Okay. Some people might, nowadays you might simply say, okay, well, maybe we're fine with that. Maybe, okay, this is a hard task. Which of these things has straight lines? Humans, yeah, they can do it. They can't do it quickly. Humans have to do it through some sort of step-by-step process, tracing through the lines. And so maybe that's an indication that if we want an artificial system to do this task, maybe we also have to have the artificial system have some way of stepping through these things. But it's definitely a stop to the idea of, or at least difficult to the idea of, okay, the perceptron can do anything. Yes, it can do anything. This is a situation where it might need to be larger than the planet in order to do that sort of task. So that's one big issue that they raised. Another big issue that they raised, what are the magnitudes of the weights? This is something that nowadays we don't really, or sometimes we care about, but it was certainly really important when they were physically implementing this as with sort of motors that were twisting variable resistors in order to change the connection weights. If that's the way you're going to do things, well, you're going to have a problem, though, even if there are weights that will do your task, and there's a reasonable number of them. If one of those weights is 0.000001 and another one of the weights is 4,723,000, it's going to be really difficult to have a physical device that can handle that sort of range of weights. Okay? Even in sort of modern computers with 32-bit floating point numbers, there's limits on what sort of range we can implement. So there might be solutions that we just can't get at just because of the difficulties of representing these weights. Other things that they talked about in the book were, well, okay, fine, the learning might not take an infinite amount of time, but it might still take a long time. They showed some examples of that. And there's some discussion also of this non-unique answers issue, that it'll find a solution. There's an infinite number of lines you can draw between two data sets. Can we say anything about which ones it's picking and whatnot? Cool. So that's a perceptron. One reason that I'm focusing a lot on this is a lot of these questions and issues that are sort of coming up here are the same ones that we're going to be talking about throughout the course, especially this idea of where do we get features from. I will also comment that the last layer of almost all modern neural networks is pretty much just a perceptron. And one way you can think of all of modern, newer AI is just ways of dealing with this feature problem, of coming up with a good set of features, so that something as simple as this perceptron, simply saying, okay, let's do a weighted sum of these values, can do the task that we want. Okay. All right. Oh, right. Yeah. So there's that diagram for the non-unique answers. So that's what we have for today. If people are looking for interesting reading, I do like the Rosenblatt paper. It lays out a lot of these ideas and sort of a lot of the same issues that people are running into right now. So it's an interesting sort of historical thing to look at. For projects, so this course does have a final project. It's in groups of either 1 or 2, so just to having people start thinking about ideas for that. One thing is just go through the Minsky and Papert book and see, are there interesting tasks that you could try solving, like using a perceptron. Sure, first, because on a modern computer you can do a bigger perceptron than they had access to, and run it a lot faster. But then also apply some of the later techniques that we'll see throughout the course to the same task. Okay. And then similar, you could also look at the Mark I perceptron, like the things that they ran on the actual physical machine, and compare to other methods. Okay, so that might be worth looking into. All right, that's where we've got for now. In the next lecture, we're going to go on to take a very similar mathematical approach and say, can we take the sort of math that we're talking about right here, and can we approach this problem in a different way? Is there a different way of getting these weights, and does that give us insight into this problem? Great, we'll see you later.